Welcome to our webinar. My name is Paweł. I'm from Fischione Instruments, and we have with us today Daniel Perea from Pacific Northwest National Laboratory.
Good morning. Welcome to be here.
We will talk today how to accurately prepare the air-sensitive samples for advanced atom probe tomography analysis. So before we start, please remember to use Q&A to submit your questions. All questions will be answered at the end of the presentation. So this work was done by Cecil Bonifacio from Fischione Instruments and Daniel with help from myself, and unfortunately Cecil cannot be here with us today. So me and Daniel will be presenting that webinar. So let's start our presentation. And first, I will tell you about our motivation for this work. Second, I will describe our air-free sample preparation workflow. Then I will focus on results, and I will finish with conclusions. There are many air-sensitive materials in many applications. For example, lithium, sodium, and solid-state electrolytes in ion batteries research and development. Also, magnesium in aerospace and automotive industry. So if you expose those materials to oxygen or humidity, their microstructure and properties can be altered, leading to not accurate observations and conclusions. In this work today, we will focus on magnesium sample preparation and structural analysis. So as you can see here, from the results of atom probe tomography done from sample prepared at ambient atmosphere. If you expose magnesium to air during sample preparation and analytical investigation, you will get significant oxidation, as you can see here. Oxidation can affect sample integrity, so influence microstructure analysis, interpretation of the results, and conclusions. In addition, the use of Ga FIB for sample preparation induces structural damage from gallium ions interaction with the material, as you can see here. The microstructural details can be easily hidden by oxidation and gallium ions implantation. Like you can see here on magnesium prepare under ambient conditions. In this webinar, we will discuss how to prevent oxidation and remove FIB-induced damage during sample preparation, allowing accurate microstructure investigation. So here we have our full-scale characterization workflow done at NanoMill. You can see here that we can go from bulk sample preparation and SEM characterization like EBSD, EDS, through the FIB sample preparation of APT sample to APT analysis without exposure of study material to air atmosphere. So all transfer between all that different instruments here are done under control environment. So let me explain now in details all the steps of this control workflow. So first, we study a bulk sample. So the sample was loaded in the glow box to add a vacuum inert gas cryogenic transfer capsule and then transfer to argon broad ion beam milling system model 1060 to TrionMill. After the preparation, sample was directly, without passing by glove box, transfer to FIB SEM for observation and FIB sample preparation. Once SEM characterization and FIB sample preparation were finished, sample was transferred to NanoMill system to remove the gallium index damage, and the final gallium-free APT sample was transferred to APT for measurements, and this transfer was done using PNL transfer hub, as you can see here. So let's now focus on bulk sample preparation and investigation. So samples of magnesium were prepared using model 1062 TrionMill argon broad ion beam milling system. The instrument is fitted with 3 ion sources, allowing ion milling using energy from 10 to 0.1 kV, has adjustable beam size and beam position possibility. TrionMill can be fitted with Corom transfer capsule, as you can see here, allowing direct transfer from preparation to FIB SEM without passing by glow box. Sample can be transferred as vacuum or inert gas. Sample also can be actively cooling using liquid nitrogen during the transfer. So if our example today will focus on magnesium alloy exposed to high stray dynamic deformation. Here you can see sample before deformation as received with oxidation on the left, and after argon ion milling using model 1062 on the right. As you can see, we can nicely observe the magnesium microstructure and obtain high quality EBSD pattern, allowing accurate EBSD measurements. On this slide, you can see grain boundaries EBSD map. The twins are in the red. The high angle grain boundaries are shown in black, and the low angle grain boundaries are shown in blue. The EBSD results show the magnesium deforms by twinning, and while exposed to constant load, the secondary twinning occurs within primary twins, as you can see here. These serve as nuclei for dynamic recrystallization, and we can observe the shear band formation, as you can see here, with fine dynamically recrystallized grains. On this slide, we can see grain reference orientation deviation EBSD map showing the formation area colored from green to red and recrystallized area in blue. We can clearly see that fracture appears along the shear bands. So you can see it's clearly here. A very fine recrystallized grain structure is observed in the shear bands and around the cracking. This fine grain should improve material ductility and resistance to fracture. So why the fracture appears along recrystallized area? This question led us to do APT analysis. So to answer that question, we prepared APT samples using FIB from shear band area. So they are marked here. We lift out several samples with this shear band area with the fine microstructure. We are targeting specifically triple grain boundary junction to investigate the role of grain boundary on cracking mechanism in magnesium. Now, let me explain the APT sample preparation. To remove the gallium FIB damage from APT sample, we use model 1040 NanoMill post-FIB sample preparation system. The NanoMill is an argon beam milling based instrument. The beam size is about 1 micron size. The system is using ultra-low milling energy down to 50 eV and currents about tens of picoamps for material removal from APT on TEM specimens. We use transfer capsule to transfer sample under control environment, can be vacuum or inert gas, between NanoMill, glow box, and APT system. As you can see here on that image, in NanoMill, sample can be observed using secondary electrons. You can see here APT needles, which can be very easily targeted using a milling box in red, and the bin will scan sample only within that box that you will define over your sample. You can do that at different magnification and different milling angles. The milling angles can vary from 0 to plus minus 15 degrees. So let's look at some APT results. So first, APT sample prepared without NanoMill. First, as you can see here, we do not see magnesium oxidation after control environmental workflow. As you can see here also, after FIB preparation, we observe a lot of gallium everywhere. You can see magnesium atoms in pink and gallium in green. Gallium damage sample structure by ions implantation and amorphization by creating vacancies and atom displacement. These alternate sample microstructure and influence APT measurements. So now let's look at APT sample preparation with NanoMill. So the same as previously, we do not see magnesium oxidation after control environmental workflow. However, when the NanoMill is integrated in the workflow, we observe significant gallium removal, as you can see here. Less gallium in the sample indicates less gallium-induced damage. And indeed, we observe a triple grain junction with a grain boundary going along the sample, as you can see here, the grain boundary, and we have grain 1 and grain 2. And due to strong affinity of gallium to magnesium grain boundaries, we observe gallium segregation at grain boundary. As you can see on that movie here, you can see nicely the penetration of gallium, the grain boundary. This phenomenon has also been observed in case of aluminum alloys. So less noise from gallium induced structural damage allow us study of trace elements in our sample, as you can observe on those results. The observed trace elements are aluminum and manganese. They can form about 20 nanometers precipitates, as you can see here. And we clearly observe aluminum grain boundary segregation. You can see it here. So now you can link this observation to the properties and answer the question why we observe cracking propagation in recrystallized small grain area. On that illustration, we can clearly see aluminum at the grain boundary and aluminum manganese precipitates. Some of them are very close into the grain boundary, as you can see here. So aluminum segregation at the grain boundary favors cracking. The grain boundary precipitate can also reduce overall ductility of the material, and precipitates can create stress concentration at interface with matrix with which during mechanical loading can initiate cracking. So cracking propagates along grain boundaries leading to intergranular fracture observed by SEM and EBSD measurements. So now I will go to our summary and finish with conclusions. So in presented work, we show that control environmental sample preparation and analysis allow us in-depth interpretation of air-sensitive material. EBSD analysis of magnesium sample prepared by broad ion beam milling revealed deformation as well as fracture along the shear bands. A very fine grain structure was observed in shear bands and around the cracking. The gallium FIB preparation from the recrystallized fine grain areas reveals structural damage to the sample by gallium implantation, which was removed by nanomilling application. APT analysis of samples show trace elements of aluminum and manganese. Aluminum was observed at the grain boundary, and we observe the precipitates, very small nanometric precipitates of aluminum manganese. The crack propagation around the grain boundaries leading to intergranular fracture, which was attributed to aluminum segregation and precipitates. So the bulk sample preparation within a controlled environmental workflow that includes broad argon ion beam milling, gallium FIB milling, concentrate argon ion beam milling, and APT measurements revealed new insight to the magnesium specimen structure and properties. So with that, I would like to thank very much PNNL, EMSL to allow us to do that work. And I will move to Q&A, and hopefully we have some interesting question to answer. Oh, this is a nice question. Can you estimate how much material is removed on the bulk sample by broad ion beam milling? So in that case of oxidized material, it depends how you will keep your material. If it's only on the shelf, exposed all the time of oxygen and atmosphere conditions for the long time, this oxide can grow and grow. So it can be from 100 nanometers to a couple of microns, and those thickness you can easily remove using a TrionMill system in less than 1 hour. Okay, the next question. So what is the effect of ambient preparation and transfer in the case of EBSD analysis and APT analysis? So so with this oxidation, the sample will oxidize very easily, and you can get very poor signal or EBSD, and the indexing rate will be low, and you can miss a lot of information, especially if you're working on the deformed samples. Already deformation will reduce your EBSD patterns quality, because the heavily deformed material will have like give fuzzy patterns because there is less crystalline material. So if you add on the top on that oxidation, the signal will be much weaker, and you will lose your accuracy of indexing and interpretation after. And for APT, maybe Daniel can complete my answer, but as we show in that presentation, you can see even on that images that the less gallium on the specimen will improve overall sample quality. And also using NanoMill, we remove that damage from the sample induced by the interaction with gallium ions.
That's right. That's right. And the exposure to the ambient with a lot of that damage, you get the enhanced oxidation during an ambient transfer, and all that the gallium and the oxygen there actually we found leads to lower yield. So it lowers our ability to collect these larger data sets. It becomes more challenging. So being able to remove that damaged area leads to larger data sets where we can make these conclusions there.
I have another one for you, Daniel. Will be follow the previous question. Is there any advantage of argon ion milling techniques in APT specimen preparation?
In the case that we found here with the magnesium, we found, as I just mentioned, that we found an increase in the yield. We got less. The samples were less prone to fracture during the measurement, which led to more data collection. So being able to remove that damage from the fib and that in the ion mill, removing all that gallium damage seemed to help. So it led to more the collection of more data and better quality data. So we did find that to be the case with magnesium.
Indeed, thank you.
Mhm.
So another question I can see here is, can you use broad argon ion milling to perform post-FIB cleaning of APT samples? And if yes, if it's better, the same, or worse? So I mean, you can do it. You can use broad argon ion milling for the post-FIB cleaning, but I will answer the results will be worse. And this is from different aspects. I will go to the NanoMill and explain a little bit about the NanoMill. So in the NanoMill, we are able to use very low energy of milling and very low currents. We can usually we use like 300 EV or less, or 500 or less EV to mill of the gallium implantation and gallium damage from the sample. So this you cannot use at the using broad milling system, broad beam milling system. Because you can even if you can get the low energy, you can not get this low current. The current will be always higher. So higher current will make your beam much wider, and also you can then get the beam everywhere on your sample. So as you can see here, the wide broad ion beam will mill everywhere on that holder plus the sample itself. In NanoMill, you precisely target your sample, put the milling box where you really want, and milling will be only in that box, will be not affect any surrounding areas. So you will have no redeposition on the sample from sample holder, as you will have for sure using broad ion beam milling system. Daniel, you would like to add something?
No, that was the key here is that using the NanoMill, as Pablo mentioned, is the precision the ability to target the specimen tip, in this case, the APT specimen there in a TEM half grid, and the lower currents there allowed us to more precisely kind of polish and remove that damage. Whereas in the case of the broad ion beam, we'd really cause too much more damage on that sample than removing it. So that's all.
All right. So I don't see any other questions. So with that, thank you very much for your participation, and see you in the next webinar. Thank you.
Thank you, Paul.